This is Lab 5 for Physics 2211 at Georgia Tech. This lab is based on analyzing the motion of a slinky. First, I'll introduce the system and its surroundings, then I'll go over some key concepts. Next, I'll analyze the motion of the slinky using the tracker software. Based on the experimental data collected, I'll then create a predicted model. Next, I'll create a computational model on GlowScript, and finally, I'll compare the results of the two models created. Introduction. The aim of this lab is to observe the effects of gravitational force and drag force on the motion of a slinky, and using the experimental data collected to produce a computational model that accurately predicts the slinky's motion. The objective of this lab is to apply Newton's second law to a real-world scenario. The system for the lab is a slinky itself, and the surrounding consists of the Earth. Key concepts for this lab. This lab will be based on Newton's second law. Some of the important formulas used will be the position update formula, where R final is equal to R initial plus V average into delta t, and the velocity update formula, where V final is equal to V initial plus F net over m into delta t. F net is given by the gravitational force, the drag force, and the forces acting within the slinky. Accounting for all forces and the velocity update formula allows us to accurately model the movement of the spring. Analyzing the motion of the slinky using the tracker software. The tracker software maps the x and the y position of the slinky. The software tracks the center of mass of the slinky, indicated by the red dot on the screen. As time progresses, the slinky moves in the negative y direction, resulting in a downward sloping curve. The mass of the slinky is approximated to 0.25 kilograms. The initial velocity vector of the slinky is 0, 0, 0, and the initial position vector of the slinky is 3.8 into 10 raised to minus 2, minus 1.2, 0. The motion of the slinky in the negative y direction is a result of the net force acting on the slinky, which is mainly the gravitational force acting in the negative y direction, the drag force, which is the resistive force acting in the positive y direction. The data from the tracker software is used as experimental data, which was then used to create the predicted model. Next, I created a computational model using GlowScript. The mass of the ball was set to 0.25 kilograms, which in turn mimics the mass of the slinky. The initial position vector was set so that they could match the position and the velocity vectors of the slinky. Delta t was set to 0.1 seconds. G is the acceleration due to gravity, which is equal to 9.8 meters per second square. The proportionality constant B was set to 2.6. This was determined using the experimental data collected using the tracker software. The net force acting on the slinky is computed using its weight, which is minus mg, and the resistive force, which is the drag force acting in the positive y direction. Velocity update formula and position update formulas, according to the Newton's second law, were then used to map the motion of the slinky. I'll now be comparing the results of the experimental model and the computational model. The position versus time graphs map the motion of the slinky. Both graphs indicate a downward sloping curve. This is a result of the net force acting on the slinky in the negative y direction. The computational model accurately predicts the motion of the slinky, as the two curves majorly overlap and are very similar. The graph for the computational model does seem to deviate from the experimental data a bit. This is mainly due to potential errors such as experimental inaccuracies and slight discrepancies in the data collected. Thanks for watching.